and we should be live.
Yes, it seems so. I suggest that we wait for like one, well, I mean, maybe I can already start with the introduction. So, hello everybody and welcome to this morning's invited talk. We are happy to have as an invited speaker Bartek Klin. Bartek Klin is now a professor at the University of Warsaw, continuing a proud tradition of this university in logics. And he has completed his PhD in Aarhus in Denmark in 2004. Basically it was a thesis where he was looking for, well, using coalgebraic methods in analyzing processes equivalence and operational semantics. And this is also where his work was mostly focused on, so operational semantics and coalgebraic methods. He also continued his career after his PhD with postdocs in Edinburgh and Cambridge. And as I said, now he's a professor in Warsaw. And for the last few years, he was involved in a research program around the development of computation theory with atoms. And basically, this is also partly, at least, the topic of his talk from today, where he will talk about μ-Calculi with atoms. So, Bartek, you have the floor.
Thank you, Florin. Am I audible? Excellent. Thank you for this detailed introduction, and thank you all for coming. And good morning. It's a pleasure to be able to give this talk. I want to tell you about μ-Calculi with atoms. It's a result of a research project that I've been developing for the last couple of years, and this particular work is really based on two papers jointly written with Mateusz Wełyk, my colleague from Warsaw, and Clovis Eberhard in Tokyo. Let me give you a short plan of this talk. I will directly follow the title of this talk, which is not very long. I will first give a brief recollection of μ-calculus. I expect many of people in the room to know this, but just to fix notation and to recall the basic notions, I will recall the definitions. Then I will speak about atoms. This is perhaps less known, I suppose, so I will give a more detailed introduction to that. And well, the only word missing in the title is then will be with, and I will connect the two to speak about how the composition of μ-Calculus with atoms works, what it is good for. I will try to motivate it on the way, and what are the technical problems that arise in this combination. As it turns out, the landscape will be more complicated than in the standard μ-Calculus, and in particular, different variants of μ-Calculus that we take for granted to be equivalent, and we don't really even mention their differences very much in the theory, will become more prominent. And I will speak of not a single μ-Calculus, but various μ-Calculi in this talk. Now, I intend this talk to be easy to follow, and I will not give you any proofs of anything. I will rather focus on examples of various properties expressible in my calculi to highlight the differences of various calculi. Okay, so let me start with a brief recollection of μ-Calculus. It's a simple temporal logic, simple in the sense of having a simple syntax and semantics that describes properties of states in transition systems, essentially. And such a transition system can be seen of just as a directed graph. It could be finite, it could be infinite. That's an example of a model, of what I call a model. And additionally, for this graph to become a model, it will be state labeled with some labels from some finite, perhaps infinite set of basic predicates. this with my set of basic predicates, and some of the states, perhaps not all of them, will be labeled by these basic predicates, and then I can speak. My formulas in the basic calculus will define properties of such states. So, for example, an example of a formula will give you the syntax of the μ-Calculus by example. An example is a formula that says just P, and it means that P holds now. So the semantics of this formula, it's a subset of states in my model, and it will be the set of those states which are labeled with the basic property P. A state may be labeled with more than one property, and so that it can satisfy more than such basic formulas. Another example of a formula is the so-called diamond modality. So diamond P means that the property P holds in some successor, and just similarly, the property P or diamond P means that P holds now or in some successor. I have a brief technical question. Can you see the blue parts on the slide right now? No. Okay, that's a small problem, but let me focus. Let me persevere. So, a slightly more complex formula is a fixed point formula. This is the formula that says, okay, the semantics of this formula is calculated as a least fixed point of a certain function on sets of states. So it may be seen as computed in an approximation procedure. So we start by assuming that this set X, this formula X that we want to define, is the empty set, is not satisfied by any process. And then if we assume that X is empty, we evaluate this formula here. So if X is empty, so diamond X is also empty, is not satisfied in any state, then P or diamond X, it's a formula that's satisfied exactly in those states which are where the basic property P holds. So in these two. Yes. And then if now we assign this particular property that P holds currently to the set to X. Now we think that X is this property, and then we calculate this again. This will turn out to be a bigger property, and so on and so forth. So it will turn out to be a fixed point computation that will end up to be the final semantics, the fixed point of this procedure, the least fixed point of this procedure in this case, will be the property that's satisfied in the blue parts, in the states marked blue here, and the semantics of this formula will says that P holds in some future. P holds in some path starting from my current state. This is the property of the state that is defined by this simple μ-Calculus formula. So I showed you by example the syntax of the μ-Calculus. It has basic properties, it has propositional connectives, it has the diamond modality, and it has the least fixed point construction, and essentially it doesn't have anything more. But we can also use other operators that in fact are definable in the ones that I've already given you. For example, this is the greatest fixed point operator. And we also have the box modality that says that something happens in every direct successor of the current state, not in some, but in every successor. So for example, this formula actually turns out to be the negation of the formula that I showed you on the previous slide. And it is also calculated by a fixed point construction, except that now it is the greatest fixed point. So I start with assigning X to be the property that is satisfied everywhere, and then I decrease my semantics so that it becomes this. P never holds in any future. Okay, And this is the end of the presentation of the μ-Calculus, its syntax and semantics. By example, I will give a more formal definition later when I speak about μ-Calculus with atoms. I just don't want to give the same definition twice formally. Okay, I hope this is clear. Now, the properties that I will be interested, and people are interested in μ-Calculus and also in temporal logics in general, is, for example, it's model checking. So the model checking problem is, given a model capital K and a state in it, and given a formula, is it true that the state satisfies the formula? So for this, it makes sense to assume that the model is finite, so that it can be seen as immediately as an input to an algorithm. If it's infinite, then it had better some structure, so it can be finally presented. But for finite models, at least, this problem is decidable, and there is a naive way to prove this, but it's a very easy way. Namely, it is clearly this model checking problem is clearly decidable because I can directly compute on a finite model the semantics of every formula just by computing the fixed point formulas in particular by finite approximation. On a finite model, every fixed point calculation terminates in infinitely many steps. So that's it. Now, this is not the most clever algorithm one can come up with. And in fact, there are more efficient solutions using parity games. But I should stress, and I want to stress, that there is also a naive algorithm, sort of kindergarten algorithm, that works well in p-space. And it just directly calculates the semantics of every formula. I stress this because this naive algorithm is something that will also work in the setting with atoms, unlike parity games where I don't know. Another problem is satisfiability. And the satisfiability problem is that the only part of the input is a formula phi, and then we ask, does there exist a model, well, and formally a state in it, so that the state satisfy the formula? This is also decidable. Well, and on the first side, that there are two versions of this problem. We may ask this model to be finite or not in the satisfiability question, but they are equivalent because of something that is called the finite model property, and namely, a formula of the μ-Calculus has a model if and only if it has a finite model. And in fact, we can even bound the size of that candidate model for that satisfies a formula, which actually is the easiest way to see that the satisfiability problem is decidable, because there is a countable, I'm sorry, not the countable, a computable bound on the size of a model that is supposed to satisfy a formula. So we can just go through all of them. That's the easiest way to see that satisfiability is also decidable due to the small model property. And I recall this because this small model property and finite model property is something that will fail in the setting with atoms, and in fact, the satisfiability problem there will not be decidable. Finally, there is the μ-Calculus has some fragments that are known and liked and well studied. One such fragment is CTL star. This is a temporal logic with two kinds of formulas, state formulas, which are evaluated on states of a model of the same kind that I showed you previously, and also path formulas that I interpreted on infinite paths. And this is a fragment, although the proof that this is a fragment of the μ-Calculus is not very easy. It's not a direct syntactic translation, say inductive syntactic translation of CTL star formulas into the μ-Calculus. It's more involved than that. It goes through automata, and in fact, this phenomenon that it's not such an easy translation will show in the setting with atoms, because as I will show you, in the setting with atoms, CTL star will not be a fragment of the μ-calculus. It will encode some properties that the μ-calculus cannot. All right, so this is all I want to say about the classical μ-calculus. I'm sorry. Let me motivate the setting with atoms. So let's say that I have an infinite set of basic predicates. Okay. Now, in principle, in the definition of the μ-calculus, as I showed you, there is no limitation of the basic predicates to the set of the basic predicates to be finite. But really, there is, because every formula is a finite object, and therefore it only refers to finitely many basic predicates. But let's say that I really want to model something that refers to infinitely many basic predicates. So let's say that I have countably many basic predicates, and the intuition behind the predicate Pn that may hold or not in some state will be that the user has just input number n from the keyboard. Okay. And then let's say that I want to define the property that the current input number is input again in some future, can be input again. Okay, that the user can input the same number now and at some point in the future. Now I would like to. Now this is the formula. Now if you're familiar with μ-calculus, you can probably decipher this formula quickly, but not too many people can do that on the fly. But this, believe me when I say that this formula says that Pn holds now. Actually, there's a mistake here. There should be a conjunction here. Pn holds now and in some future. And then if I take a huge disjunction over all natural numbers, this is supposed to define the property that I'm talking about. And there's another mistake. Thank you for this remark in the chat. They should be Pn. Okay. Now this morally defines the property that I want to formulate, but formally it's not in the syntax of the μ-calculus because of the infinite disjunction. Yes. So just allowing infinite disjunctions completely uncontrolled in the μ-calculus would be a bad idea. Well, first of all, because even the set of formulas would become uncountable, and there would be no hope of any decidability results at all. So this setting with atoms is, in a sense, an attempt to give infinite disjunctions in a controlled way, so that we can retain some decidability fashion. Okay. So sorry, I didn't understand this. But the first conjunction should be and implies, no? Well, yeah, it could be an implies. Actually, it's almost an equivalent. It would be more. It would morally define the same property. I mean, the only difference is in the settings where there are some states where no number is input, and then yeah, it's. Perhaps the English prose definition was not very precise to distinguish between two formulas. Now, these kind of formulas is actually practically motivated because we might want to conceivably to model in a practical setting, to model and verify and check properties of systems that say involve password generators or nonce generators. Passwords are things that can be compared for equality. And then we might say that the system never crashes, well, unless, there's a caveat here, unless the password generator generates the same password twice. So really when we say that no bad state is reached, we should be formally forced to say that no bad state is reached on any path where no password has ever been generated twice. Because if that happens, the system may crash, and we don't care. We just should trust the password. So this is the kind of property that I think it should be clear that is related, is sort of similar to the property that I've defined here, that we might want to formulate. Okay. So this problem has been recognized and it's been studied in the literature. And generally, it's the subject of temporal logic with data items, where some data can be compared for equality or perhaps for some slightly more complex relations. So there is a work, that research was mostly focused around the temporal logic LTL, which is a fragment of the μ-calculus. So the most important parts are the LTL with freeze quantifiers and LTL with constraints, where we can use constraints on some data values from some infinite data domain as parts of our μ-calculus formulas. And this is all very, very nice work, and it's all subtle, and it's not easy to come up with the right syntax and semantics and with the right restrictions so that model checking and satisfiability on this logic remain decidable. But this is what these people have been focusing on with success. So with some subtle and delicate restrictions, they are able to achieve this. Okay. There are also some approaches, such as, for example, the first order calculus. I don't know if you know about it, where they don't really care about model checking or satisfiability being decidable. Instead, they trust that for all the practical cases they will work with, they will be decided using some heuristics. So this is more an engineering approach, I would say. Okay, so this is also possible, and it has been done. This work here is the μ-calculus with atoms. It sort of sits in between. So I will, in the μ-calculus with atoms, model checking will be decidable, satisfiability will not. So some applications some applications to verifications where satisfiability or non-emptiness will be crucial will be out of the question here. But some applications where we have a concrete system and concrete property to check will still be covered in reasonable complexity. So this is what this μ-calculus will be. So let me now speak about atoms. Okay. So in contrast to these fine and subtle works on LTL with freeze quantifiers and LTL with data, the approach that we take to define a calculus to work with infinite data domains will be completely thoughtless. We will not do any thinking at all. We will take a hammer, hit μ-calculus with that hammer, and see what happens. And this hammer will be set theory with atoms. The idea there is, rather than take the μ-calculus and include infinitely many data values in that as a sort of an afterthought, as another aspect, we introduce atoms into the very fabric of the universe, beginning right from the set theory. Okay, so sets with atoms, we will start with atoms right there, do everything with atoms, and mutcalculus would be one of these things. This is the philosophy here. So formally, what we will do is I will start right from the level of sets. Let's say that I have a structure of atoms, an infinitely countably infinite set of atoms. It will be a relational structure more generally, and I fix it. But in this talk I will only speak about two of them, and mostly about one of them. So if you're not familiar, feel free to think that atoms is just a set, natural numbers, and the only relation that I'm ever allowed to use on these numbers is equality. So no addition, nothing like that. It will be just nothing. I can only compare atoms for equality. So it's slightly more structured setting is a total order of atoms, and then I would want to think this total order to be the order of rationals. There are other cases, such as the random graph, infinite dimensional vector space of atoms, and so on. But let's in this talk I will only focus about these two. And really, you're welcome to think about just this one. Okay. Now, if I start from this infinite structure, I build I build set theory on that. So I use the cumulative hierarchy of sets. There are a few equivalent ways of introducing sets with atoms. This is a set theoretical one. It's a theoretic one. I use a von Neumann hierarchy of universes, where at the 0th level I have nothing, and then at each next level I throw in atoms at each level. So every atom is always a set. Okay, it's an atom is an empty set because it doesn't contain any elements, but it is a set. And then I take the power set of everything at the previous level, and then at limit ordinals I take everything I've collected so far. So this is modulo this atoms bit. This is the standard von Neumann construction of the universe of sets. I just throw atoms everywhere. So what happens here really is that so far what I've done is I constructed a universe of sets built of curly braces and perhaps atoms at the bottom somewhere. Okay. And then the important thing is that if I take the group of automorphisms of the structure of atoms, it acts in a canonical way on this universe. So for the case of equality atoms here, automorphisms are just arbitrary bijections, arbitrary bijective renamings of atoms. And it's clear if I have a renaming of atoms, and if I can apply it to a set in this universe just by renaming every atom that sits there at the bottom, and I get another set. Okay, so this, and it's a group action. Right. The crucial definition here is the notion of support. So let me say this slowly, because this is a definition that you really need to see twice to understand. So let me tell you the definition twice. So we say that a finite set of atoms supports something in the universe if whenever I have a bijective renaming of atoms that happens to fix everything in that set S, then it also fixes the object X. Okay. Then we say that the set S supports X. That's the definition. Examples. If I take this two-element set of atoms, A and B, it supports the atom A, because if I have any renaming that fixes A and B, in particular, it fixes A, so there you go, it fixes A. It also, this set also supports B, supports the singleton of A, supports this thing, and in general, it supports every object that only ever uses atoms A and B anywhere. Okay, so that's one way to understand support. But the definition of support is more clever than this. It's not just.
So Bartek, there's a question in the chat, please. If you
is there.
Should x pi be pi equals pi be x pi equals x instead?
Oh yeah, I'm sorry. Ah, wow. Sorry about this. It should absolutely be X. Thank you for this. It's a typo. Thanks, Antoine. Right, where was I? Ah, okay. There are other sets that contain other atoms than just A and B, but they are still supported by this set S, this two-element set A, B. For example, the set of all atoms different than A. If you apply any renaming that fixes A in particular, it becomes the same set still. Okay, its elements might be shuffled, but as a set, it remains the same. So this set is also supported by S. And really, the right intuition is not that an object is supported by some set if it only contains atoms from that set anywhere, but rather we should say that an object is supported, we should think that an object is supported by S if it can only be defined or spoken about without mentioning any specific atoms other than those in S. So for example, here I defined the set just mentioning A, therefore it is supported by A. Now this is all for equality atoms, but for ordered atoms, some more clever sets can be supported. For example, the open interval of all atoms between A and B are also supported by A and B. And also some relations, such as this one, marked in blue here, that only ever refer to the atoms A and B, which are now rational numbers over ordered atoms. This is also supported. And in the set theory with atoms, the restriction that we impose is that we only ever consider, and we consider illegal, only those sets that are hereditarily finitely supported, meaning that we only consider sets that have some finite support, and such that every element has some finite support, perhaps a different one, and every element of an element has some finite support, and all the way down. Okay. Right. A special case of being finitely supported is the property of being equivariant. We say that an object is equivariant if it is supported by the empty set. Now, this is a useful notion to think about because there is one parameter less to think about, the support, and examples, and there are plenty of useful examples of equivariant things. So, for example, so these sets are all equivariant. This is a set of atoms itself, the set of k tuples of atoms for some number k, the set of k tuples of pairwise distinct atoms, which I denote like this, the set of sets of atoms of size k, which is a bit more symmetric version of this one, the set of words over atoms, and so on. These are all equivariant. The set of finitely supported subsets of atoms, the set of finitely supported infinite sequences of atoms, these are all the set of finitely supported functions from x to y for some equivariant sets y. These are all equivariant sets. So there's plenty of examples here to go on. For ordered atoms, again, some more sets become equivariant, such as, for example, the set of increasing k tuples. Now, with over equality atoms, we cannot say anything about increasing. And there is a relation, there is a definition of what it means for a relation or function to be equivariant. Now, these are not new definitions; they are just unfolding of the definitions of equivariance. So, for example, a function is equivariant if it commutes with an application of any and there is a typo here again. This should be fine. Okay. If it commutes with the application of any automorphism. Now, the final piece of information about atoms will be orbit finite sets. I will give you a simplified equivariant version of this notion. So, if I take any element in the universe, then its orbit is the set of all elements that I can get to by applying some atom automorphism. Okay. And then every equivariant set is the union of its elements' orbits. That's easy to see. And well, a set I would call a set orbit finite if it is orbit finite. Yeah? If it is a union of finitely many orbits. Examples: these sets, the set of atoms and the set of sets of atoms of size k. These just have single orbits. You can get from any set of size k of atoms, of equality atoms, you can get to any other. Now, the set of pairwise distinct tuples, this is a single orbit set for equality atoms. For ordered atoms, well, there's the different ordering, so there's exactly k factorial orbits there. And this is also orbit finite. And sets such as A star, the set of words, or the set of finite subsets of A are not orbit finite because, well, for example, for words, two words that have different length are necessarily in different orbits. Okay. Now, orbit finite sets have good properties. They are closed under finite products, finite unions, even orbit finite unions, taking equivariant subset and so on. Importantly, orbit finite sets are also representable. They are definable by finite means, so that they can be seen as inputs to algorithms. I won't give you any details on that, but they are essentially defined by formulas. So a typical single orbit set is something like the set of quintuples of atoms such that the second one is equal to the fourth one. So this is just a finite way of saying what a set is. and then we can compute on that. So there is a recipe for adding atoms to everything in mathematics, essentially, but in particular in computation theory. The idea is you take your favorite definition, you replace all sets, relations, functions, and everything with sets with atoms. If you're modest, you can content yourself with equivariant ones. You replace every occurrence of finite with orbit finite, and you look at what you got, and you check if your theorems still hold. Sometimes they will, with the same proof as in the classic case. That's not interesting. Sometimes they will fail, and that's somewhat interesting. And sometimes they will hold with a more interesting proof, and that's also then interesting. Well, we should take it with a pinch of salt. In particular, thinking about where exactly the word finite appears in your definition, that sometimes takes some design decision. So this has been applied to various things, in particular in computation theory. So with our automata with atoms that turned out to be register automata, if you know them, grammars, Turing machines, while programs, functional programs, constraint satisfaction problems, vector spaces, and what have you, and also the μ-Calculus. Okay, so let's apply this recipe to the μ-Calculus. First of all, models. And it will be a completely straightforward thing to do. So I will actually go very quickly through that. So now a model with atoms. Now I have an equivariant set of basic predicates, not just set, but a set with atoms. But really, in all examples that I will speak about, it will be just a set of atoms. Very, 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 very basic predicates. And now a model with atoms is what it used to be, except that now the set of states is with atoms. It could be orbit finite, it could be orbit infinite, just as in the classic case, it could be finite or infinite. And then a finitely supported relation, or really in all examples, it will be an equivariant relation, a transition relation, and an equivariant, let's say, or finitely supported, more general function that to every state gives not a set of, not an arbitrary set of basic predicates, but a finitely supported set of basic predicates. It will usually be just finite. For example, I can consider a model where states are words built of atoms. A transition is just appending a letter to a word, and then every word satisfies the basic predicate that is equal to the last letter in it. So this is what this model looks like. And the basic predicates are marked, well, two of them are anyway, are marked with blue and green. This model is not orbit finite because the set of states is not orbit finite. Okay, and it's a well-defined model. So this is what models look like. And for the formulas, the modification to the syntax of the μ-Calculus will be very, very straightforward. Namely, I keep everything as it is, except that there is one point in the syntax of the classic μ-Calculus where I notice the word finite, if I squint hard enough. And this is the finite disjunction. And I replace it by orbit finite according to my recipe. So what happens here is I allow the junctions of orbit finite families of formulas. Okay, really, in practical examples, typically the families of formulas that I will take the disjunction of will be of this form. It will be indexed by, say, atoms, by single atoms, and then I can use this more intuitive notation, and also more reminiscent of the Fries quantifier from the LTL work. Now, formally, with this restricted syntax, I need some to speak about positive formulas so that fixed points are well defined. If you know μ-Calculus, you know what I'm talking about. If you don't, you probably don't notice the problem. So let's just go ahead. There are some standard abbreviations so I can still speak about the greatest fixed points. Well, conjunction and also the box modality. This is all completely standard, as it works exactly as in the classical case. So as you see, the syntax is essentially the same as in the atomless case. And an example of a formula is now with the same typo as before, is now the property that that I wanted to mention, the property that some atom holds now and in some future. Now, formally speaking, what I've done here is two versions of this calculus, because we have two atom structures that I speak about: the equality calculus and the ordered atoms calculus. The semantics is completely standard. Let me just say that let's not look at the slide very carefully. Let's just say that all these equations are exactly as in the classical case, except this one, the orbit finite disjunction, and this is what you would expect. This is a completely easy equation that does nothing interesting. Yeah? This is just disjunction. That's it. That's the semantic. So it's a very simple definition. Examples. Let's not decipher this example very carefully, but let me just phrase in English the kind of property that I can express. So this formula says that some predicate, some basic predicate holds now again in some future, and with the same annoying typo again. This says every reachable state has some successor, has some direct successor for which some basic predicate holds. Finally, this says on every path, no basic predicates holds more than once. Okay, so this is the kind of property that I can express with this syntax. All right, now properties. The first thing is that model checking on orbit finite models is decidable. That's good. And the proof is, again, as in the classic case, I can use the naive fixed point computation algorithm. This is marginally more involved than in classic case, because you need to argue why this fixed point computation, why fixed point computation stops, given that now we have infinite models, but they are orbit finite, so in fact they stop after finitely many approximation steps. Okay, so model checking is decidable. On the other hand, satisfiability is undecidable, and in fact it's undecidable even for the LTL understood as a fragment of this calculus, LTL with atoms. And the proof is Thomas Schwentig in the room? He invented the proof. Encoding of Turing machines in the universality problem for register automata. This is exactly the same construction used here. Another property is that we can also speak about CTL star with atoms, arising from CTL star in exactly the same way as I did. So I just replace binary disjunction with an orbit finite one. And in fact, it turns out that this is not a fragment of our mh-Calculus, and it has undecidable model checking even. So it's not a very well thought, well behaved logic. The mh-Calculus with atoms that used to be more expressive, now it's not exactly more expressive, it's incomparable, but it also has some better properties. It has decidable model checking. Also, orbit finite model property fails. So there is no hope of a finite model property for this setting, that's clear. But you would hope for an orbit finite model property, but it's not true. And this is an example. The property that a conjunction of two properties that I showed you 3 slides before, in particular, look at this one. On every path, no basic predicate holds more than once. This has a model where the set of states is the set of words built of atoms, but not all words, just pairwise distinct words. This is an equivariant set. That's fine. It's not orbit finite, but it's equivariant. And then if we restrict to these words, then this model actually satisfies this property, and also this one, as it turns out. But it has no orbit finite models. It's not very hard to prove. So this is one kind of a property that fails. Another annoying thing. So now I'm going to speak about annoying things. An annoying thing is that the language, it is a fact that the μ-calculus with ordered atoms is more expressive than the calculus for equality atoms. And if you look at it, I mean, it sounds like a moronic statement because, well, obviously it is, because it concerns a richer class of models, ones that can be defined using order on atoms. But in fact, it's more subtle than this, because if you look at the property, some successor satisfies infinitely many predicates. Some direct successor satisfies infinitely many basic predicates. This is a property that doesn't refer to the order of atoms in any way. And in fact, formally, it is invariant under arbitrary bijections of atoms. So it is conceivable that it could be defined by a formula in the equality atoms, the μ-calculus, right? But it's not. It's not expressive in the calculus over equality atoms. It is expressive in the calculus with ordered atoms because it's not hard to see that if you want over ordered atoms, if you want to have infinitely many predicates satisfied, that there must be an interval of basic predicates satisfied. And this is what this property, what this formula expresses. And in fact, but as you may imagine, non-expressibility results are rather subtle and painful. And there will be a few of them in the next few slides. The proof is not very easy, and it uses so whenever I say that something is not expressible in some calculus, the tool in the proof is always a suitable notion of bisimulation. We prove that you come up with a notion of bisimulation. You say that two models satisfy the same formulas if and only if they are related by some bisimulation, and then you show bisimilar models that so that one of them satisfies this property under consideration and the other one does not. This is what the proof looks like in all inexpressibility results here, and they are not very easy. Another property, problematic properties. Okay, this is a chain. A chain is a path. Is an infinite path, so let's say that every state on this path satisfies some basic property, let's say an atom, and then I call this a chain if the basic property is equal in these two states, is also equal in these two states, is equal in these two states, and so on. Okay, I hope that the drawing explains why the name, that explains the name rather well. And then the property that some path from the current state is a chain turns out to not be expressible in my μ-calculus. Now this is annoying, especially if you come from the community of register automata. You will find this extremely disappointing, because this is a very easy property from the perspective of automata. If you have a path, there is a very simple deterministic automaton with two registers that recognizes this. So the fact that this is not expressible, it is a problem, but it turns out that it is expressible in the vectorial version of the μ-calculus. Now, let me very briefly recall what a vectorial μ-calculus is. It is a notion from the classical theory of μ-calculus, and the idea is that in the vectorial calculus, you don't define a single variable by a fixed point. Instead, you define a few of them, finitely many of them, by simultaneous fixed point construction. So what you do here is you define a bunch of variables by simultaneous fixed point. These formulas can refer to all of them, and then you choose one of them, and that's the semantics of your formula phi. So this is the vectorial calculus. And in the classical case, the vectorial calculus is expressively equivalent to the standard one. Okay, so that's why it's perhaps not such an okay. It is important, but it's not as important as it could be as a variant of the μ-calculus. But now with our recipe, we can say, aha, there is now another place in the definition of the μ-calculus where the word finite appeared. Okay, namely, there is finitely many variables that I'm just defining by simultaneous fixed point definition. So now, what happens if I replace this by orbitally finitely many? Okay, just I still hit the calculus with the same hammer. It's just that for the vectorial calculus there is another angle to hit it with. So now what happens here is that I allow myself to define orbit finitely many properties in parallel, or another way to look at it, that I really define finitely many properties, finitely many variables, but they are parameterized by atoms. So I define a whole family of properties parameterized by atoms, and it turns out that the chain property then becomes expressible. I won't decipher this formula very carefully, but let me just say that I define a fixed point of a whole family of x's parameterized by atoms, and then the idea is that you can pass these atoms as a parameter to the same definition, and then you're allowed more flexibility. Okay, so then chain property is expressible, which means that the vectorial calculus in the atom setting is strictly more expressive than the, let's call it scalar one, non-vectorial. And it turns out that model checking on orbit finite models of this extended vectorial calculus is still decidable. Another and final, I promise, problematic property is something that I call fresh path. The property is this: on some path, no basic predicate holds more than once. And that's a nasty one. It is not expressible, even in the vectorial calculus, even for ordered atoms. And again, this is one of the harder proofs in this whole work. Now, let me just recall that the similar property that on every path no basic predicate holds more than once is expressible. Okay. So, and I have already given you an example on previous slides. So this one is okay, but this one is not expressible. There exists a path so that no basic predicate holds more than once. So we've worked on this for a while, trying to understand how to extend the μ-calculus so that it becomes expressible in a sort of syntactically economic way. And this is where I break my promise. So I promised that I will just take a hammer and hit the standard definition of the μ-calculus with a hammer and see what happens. Now, actually, it involves some thinking. What happens on the next slide? The idea is to extend the syntax of the atomic μ-calculus with a simple operator that doesn't have any non-trivial subformulas. It looks like a basic predicate. And this says the atom A has never appeared in any predicate so far. It is a history-aware operator. Okay. Now it means that the semantics of a formula is not evaluated just in a model, in a state of a model, but in a model together with its history. This history here is H. It's just a finite set of atoms, and then I redefine my semantics. I extend it so that, well, this is clear. So this formula holds in some state in if the atom is not present in the history, and then I need to build these histories properly and that the semantics of the diamond modality cares about that. But the intuition is that this is called fresh A. A is fresh. And now it's easy to see that this expresses the fresh path property. This is a formula. It's not a big deal. A short one. And it turns out that model checking on orbit finite models is still decidable. And that's a hard part. Now it becomes difficult because now my semantics is evaluated in the context of some histories, and the set of these histories is not orbit finite. So it's not clear that any fixed point construction will terminate, or even that these histories can be finitely presented as objects in my algorithms. So this is perhaps the most difficult proof that we've done but it turns out to be still decidable. It's still in p-space, so the complexity is not worse. But the fact that any algorithms works at all is not easy. And we've applied it. So now that we have this ability of speaking of there exists a path where no password is generated twice, we can formulate the security, for example, of the Needham-Schroeder public key cryptographic protocol. So this is a key exchange protocol that has Alice and Bob, and Eve tries to impersonate Bob in the eyes of Alice. And we can actually formulate this system consisting of Alice, Bob, and Eve as an orbit finite model. And the security of this model is expressed as a formula in the history-aware version of our μ-Calculus with equality atoms. Equality is fine because in this property, nonces, in this protocol, nonces that are generated are only ever compared for equality. And this formula famously fails because, well, the Needham-Schroeder public key protocol is vulnerable, as was shown long after the protocol was suggested. It falls to a man-in-the-middle attack, and this, in fact, this formula fails for the model. And also, there is an improved version of the protocol that can also be defined as a model, and there the formula holds. So as you expected. Now this is okay. So it's an example of the kind of practical applications that can be worked out with this μ-Calculus, where we are allowed an infinite source of nonces that can be compared for equality. So to conclude, we have this extended calculus with atoms. Some good things happen. Model checking is decidable. Some bad things happen. Satisfiability is not, and CTL star is not a fragment. Well, CTL star is to blame, because then even model checking is undecidable. And also complications happen. So vectorial calculus is strictly more expressive, which is a bit frustrating. And then because it's just easier, more difficult to read. And then the history dependence is a further extension, and it's a bit annoying that you need that. Future work. Well, we don't know very much about orbit finite parity games. There is a standard correspondence of mu formulas with parity games, and it holds in the orbit finite setting. So there is a notion of an orbit finite parity game, and the correspondence is okay, but we don't know anything about the algorithmic properties of these orbit finite parity games. So the question is it possible to improve the complexity of the model checking problem by using orbit finite parity games instead of the naive solution of explicitly calculating all fixed points? We don't know. Also, I think that the decidability of model checking, there's a feeling that the horrible proof of the decidability of model checking for the history-aware automaton in particular would be much simplified if we ditched the syntax of the μ-Calculus altogether, and instead we worked with alternating register automata with some notion of history awareness. That's not done, but I think it should simplify things quite substantially. And finally, we should perhaps, everything that I've told you is just about equality and ordered atoms, but the theory of sets with atoms allows other structures, and this is not what we've done. Perhaps there's no practical motivation for considering nonces that form a graph, but it might be interesting from the theoretical point of view. That's all I want to say. Thank you.
Thank you very much for the very nice talk. The audience is clapping. Sadly, you can't really hear them, but
I can see some clapping. Thank you.
Yes, at least that's a good thing about it. So I will clap for them. I hope you can hear me. So are there any questions from the audience? Yeah, there are some raised hands. So I saw first Eric. I will ask you. So I asked you to unmute so you can ask the question yourself.
Okay, thank you very much for this very nice talk.
I have the following question. You have several variants of this μ-calculus with atoms, and in morally this poses the question of what is the right one. And one guiding principle might be whether there is a Shannon-Valukiewicz type theorem for any of them, that is a bisimulation invariant fragment of monadic second order logic. And you have a notion of bisimulation, so this might be a reasonable.
Yes, excellent question. I should have put it in the to-do list. Absolutely. It's a very good question. I don't know. There is a notion of bisimulation. Actually, there are two notions of bisimulation. There is a different one for the scalar calculus and for the vectorial one. And yes, the Shannon-Valukiewicz theorem is something to look for. Yeah, thank you.
So thanks for the question. Now I will ask Carolina to unmute and ask her question.
Hello, thank you for the lovely, very clear and instructive talk. You mentioned that if you add atoms to automata onwards, I imagine, you get register automata.
Yes.
Now the μ-calculus is the same thing as tree automata. So do you then get the same thing as tree automata with registers? Or is there some difference in expressivity you have here?
So that hasn't been written down, but at least in the, so I guess, but it must be true, is that the vectorial calculus corresponds to tree automata, okay, with registers. Now, the scalar one is a bit restricted version, and I don't know exactly what kind of automata it corresponds to. And the history-aware one, that hasn't been worked out.
All right.
But I think that the correspondence that you get between automata and μ-calculus, the classical one, is translated to a correspondence between register automata and the vectorial version of μ-calculus. Actually, this is the correspondence. This is the way you prove the correspondence for the classic version as well. You start with the vectorial one, and then you massage the formulas into the scalar one. So this massaging doesn't work in the setting with atoms, but the correspondence, again, as I said, it hasn't been written down. It was only be scribbled on the whiteboard, but it's not true.
Thanks.
Thanks, Carolina, for the question. I will ask now Thomas to unmute. And
yes, thank you very much, Bartek, for this very nice talk. In fact, I had the same question, and my intuition was that they were not equivalent, but probably I'm wrong. But so I have a second question, which is you gave two examples of protocols that have a orbit finite model, and I wanted to know to which extent like more advanced protocols fall into this category. So until what is the limit of applying these techniques for proving the correctness of protocols?
Oh well, that's not so. What kind of protocols do you think about? Oh, I think you've muted yourself again.
I think I have to ask
you. Muted.
Yes. Did I mute him?
Sorry,
I don't think so. But I will ask again to.
Yes, so I know I mute myself as soon as I've finished speaking. No, I'm not an expert in protocols, so I don't know, but there are certainly many more, and I'm a bit afraid when I see these techniques that as soon as some approach in protocols are used, suddenly you don't fall in the category anymore of orbit finite models, and then there is nothing you can do. Right. So
I guess the intuition should be this: for a protocol to be an orbit finite model, it should be that in every state you only ever keep a bounded number of, say, nonces or passwords. It should be bounded by 7, okay, for some number 7. And other than that, well, you're not supposed to do anything cleverly algebraic with these passwords. So any any sophisticated cryptographic analysis with side channels and checking the length of a password or the third bit of a password, that's out of the question. If you satisfy these, if you only ever compared passwords for equality, or perhaps if you compare things like timestamps for order, this should be fine, I think.
Okay, are there any other questions? So there is a question by Alex, so please.
Yeah, so thanks, Bartek, for the talk. So maybe this is related a little bit to Thomas' question, and it's a very basic question, but your decidability results for orbit finite models then imply, and maybe it's obvious, but it's just not clear to me, imply that you have some finite way of representing orbit finite models. So
yes, that's I said it, but I didn't put it on the slide. Yes, I do.
Right.
They are finitely presentable.
And is there some sort of interesting grammar or something that generates all orbit finite models and only orbit finite models or something like that?
Well, so orbit finite sets are exactly those that are definable in the sense of model theory in the theory of theory of atoms. So, for example, an orbit finite set over equality atoms is exactly these are exactly those sets, relations, and so on that are definable by first order formulas over the theory of equality. So you can just represent your orbit finite models by formulas and compute on that.
Yeah, thanks.
I didn't mention the connection of to model theory at all, but it is quite a strong one.
So thanks. It seems that there was a question at some point from Damian. If he wants to ask, I asked him to unmute.
Oh, okay. Thanks.
I apologize that I didn't see you at the right moment.
I'm not sure if it was. I tried to raise hand. Okay, I had a comment in this direction. You suggested, well, find your preferred theorem and try to adapt it to atoms, because at some moment you mentioned parity games as a tool for model checking, but just introduction of parity games is well, for some of the parallels, just rephrasing the problem. Yes, what is essential behind this tool is determinacy theorem. Yes, and in general, this finite state determinacy is underlying many decidability results in this area. So the natural question is if there holds something like finite orbit determinacy theorem, maybe, or infinite games. You think that?
So determinacy means that exactly one of the players wins the game.
Determinacy to core just this, but what is essential is a finite state determinacy, that if the game is defined, the condition is defined using well, classical way, they're using finite description, like for example regular languages, then the winner has a strategy that uses finite memory, or maybe no memory at all, like in case of parity games. But finite state determinacy is essential.
I see. So this I haven't checked. It's a very good question. Thank you. The determinacy as it is holds for very general reasons, but what you said I haven't checked.
Okay, are there any other questions? So I don't see any hand being raised now, so I think we can actually end this session here. Thank you all very much for the lively discussion, and many thanks to Bartek for the excellent talk. So I would invite all of you now to the Gather Town of CSL, especially to the Speakers Corner, where this discussion can continue. And yeah, thanks again, and see you in the next session and in the